Welcome to the Explainer. You know, if you've ever studied physics, you've probably heard of a certain legendary textbook. It's filled with problems that don't just test what you know, they challenge how you think. Well, today we're going to crack open one of its most clever puzzles. Okay, let's get right into it. The problem we're looking at comes from Irodov's Problems in General Physics. And for physics students, this book is, well, it's a rite of passage. Its problems are famously tough because they're not just about plugging in numbers. They really force you to understand the concepts on a deep level. And here it is, problem 1.130. So we've got a body being pulled up from the ground. Now, the very first thing that should jump out at you is that the force, F, isn't constant. See how it depends on the height, y? That's a huge clue right there. It tells us this isn't a simple force times distance problem. We're definitely going to need some calculus and a bit more thinking. So here's our game plan. We'll start by figuring out the problem's hidden trick. Then we'll solve for that missing information, run the two main calculations they ask for, and then we're going to investigate a really weird, counterintuitive result that pops out. All right, let's dive into that first section and see exactly how this problem tries to trip us up right from the start. So the question wants us to calculate a couple of things over the first half of the ascent. But wait a second. How high does the body actually go? If you read the problem again, you'll see it never actually tells us the total height. And that's the first big trap. You can't find half of a number if you don't even know what the whole number is. And this is a classic Irodov move. Your first step isn't to start calculating, it's to play detective. We have to use the fundamental laws of physics to deduce this missing piece of information before we can even think about answering the real question. So, how in the world do we find that total height? Well, this is where the real physics insight comes in. This is the aha moment of the whole problem. The key that unlocks everything is the work-energy theorem. What this basically says is that if you add up all the work done on an object by all the forces acting on it, that total work has to equal the change in the object's kinetic energy. It's a super powerful tool that connects work and energy. Okay, now let's think about the body's entire journey, from the ground all the way to the top. The problem says it's hauled from the Earth's surface, which is a pretty good hint that it starts from rest. And of course, when an object reaches its absolute maximum height, let's call it h, it has to stop for just an instant before it starts to fall back down. So its velocity is 0 at the beginning and 0 at the very end. And this gives us a fantastic clear plan. Look, if the velocity is 0 at the start and 0 at the end, then the kinetic energy is also 0 at the start and end. That means the change in kinetic energy is 0. So according to our work-energy theorem, the total net work done over the entire trip from 0 to h must also be 0. All we have to do is add up our forces, integrate them over that full height h, set it all equal to 0, and then just solve for 8. And just like that, the physics gives us the answer. The net force is our applied force F minus gravity. We integrate that whole expression from 0 to h, set it equal to 0, and when the dust settles from the math, we get this beautiful result. The total height, h, is just 3 divided by that constant a. We found our missing piece of the puzzle. Awesome. Now that we've cracked the case of the total height, we can finally get back to the actual question and calculate the work done by that applied force F. So, the first half of the ascent means we're looking at the journey from y equals 0 up to h divided by 2. We just found that h is 3 over a, so half of that is simply 3 over 2a. So now we just have to integrate our force F, and just F this time, not the net force, from 0 to 3 over 2a. So we run through the calculus, it's a pretty standard polynomial integration, and we get this. The work done is negative 3 mg over 4a. And hold on a second. This is the second huge surprise in this problem. The force is supposed to be hauling the body up, but the work it did is negative. That feels completely backwards. Negative work usually means a force is fighting against the motion, like friction. So what on earth is going on here? Let's put a pin in that for just a moment. Before we untangle that mystery, let's quickly knock out this second part of the question, finding the change in potential energy. Thankfully, this part is a lot more straightforward. Right, so the formula for gravitational potential energy is just mgy, or mass times g times the change in height. The height we care about is the end of that first half of the ascent, which we know is 3 halves a. We just plug that in, and we get a potential energy gain of 3 mg over 2a. And notice it's positive, which makes total sense. As the body goes up, its potential energy should increase. No mystery there. Okay, time to go back and solve the mystery of that negative work. This is where we really have to put on our physicist hats and dig into what the math is telling us. The entire clue to this mystery is hiding in plain sight, right inside the formula for the force. Let's look really closely at that little term in the parentheses, ay minus 1. At the very beginning, when y is 0, that term is negative 1. In fact, as long as y is less than 1 over a, that term is going to be negative. And what does that mean? It means that for the first part of the trip, our hauling force is actually pushing the object down. It's only after the body passes a height of 1 over a that the force finally flips direction and starts pulling it up like we'd expect. So here's the bottom line. Our work calculation is an integral. You can think of it as finding the area under the force versus position graph. So from y equals 0 up to y equals 1 over a, the force is pointing down while the object is moving up. That gives us a big chunk of negative work. Then, from y equals 1 over a to our stopping point of 3 over 2a, the force points up, giving us positive work. It just so happens that for this specific journey, that initial negative work is bigger in magnitude than the later positive work. The total sum ends up being negative. That word hauled in the problem statement, it was a clever bit of misdirection. So what are the big lessons we can take away from this amazing problem? Well, first, always hunt for those hidden variables. Often the first step isn't a calculation, it's a deduction. Second, remember that fundamental principles, like the work-energy theorem, are your best friends for finding that missing info. Third, making reasonable physical assumptions is a key part of problem solving. And maybe most importantly, when you get a weird, counterintuitive answer, don't just assume it's wrong, dig into it. That's almost always where the deepest learning happens. And that's how we crack Irodov 1.130. It is a fantastic example of how a simple-looking problem can hide some really deep physical insights and force us to question our own intuition. It's a great reminder that the universe doesn't always work the way we think it should, and that exploring those surprises is really what physics is all about.